Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the energy of a satellite in circular and elliptical orbits. So let us first of all discuss the circular orbit. So let us see that this is the planet around which this satellite is revolving in a in an orbit of radius small r, where small r is r plus h. So this gravitational force will be balancing out the centrifugal force, which is mr omega square, or we can say mv square by r. So F gravitational is equal to mv square by r, and F gravitational is g m by r square, and that is equal to mv square by r. So cancelling out this r with r, mv square is equal to g m by r, and therefore the kinetic energy will be equal to this is half mv square, so it would be g m by 2r, and the potential energy will be equal to minus g m by r. So the total energy will be equal to sum of the kinetic as well as potential energy. So total energy is equal to g m by 2r minus g m by r. So total energy is equal to minus of g m by 2r. This is the total energy of satellite in the circular orbit. Now you can see that the total energy is minus g m by 2r, and the kinetic energy is g m by r, in fact 2r. So you can see that the total energy is equal to minus of kinetic energy, and therefore if we need to escape the satellite from the orbit, so to escape the satellite from orbit, we need to make its total energy zero. We need to make its total energy zero. So what we need that the total energy should be zero, and zero is therefore equal to the initial total energy, which is equal to minus of g m by 2r, and the final potential energy, now final should be zero, so we need to add the same amount of potential energy more to this satellite. So you can see that this is the kinetic energy, and this energy already has kinetic plus potential. So it means by adding this amount of energy to this energy, we have doubled the value of kinetic energy. So by doubling the kinetic energy and by making the speed of satellite root 2 times of the previous value, which means by increasing the speed or by increasing the speed by 41%, because V new is equal to root 2 times of V old, and root 2 is 1.414 V of V, and therefore we can say that delta V is equal to 0.41 of V, and percentage change is delta V by V into 100, so it would be 41%. So if we increase the energy, if we increase the speed of satellite by 41%, then that satellite would escape from the orbit, and therefore we can also say that the escape velocity of orbit is root 2 times of the gm by r, where under root of gm by r is the orbital velocity. Okay, so or we can say that to make the satellite escape from the orbit, we need to double its kinetic energy. Okay, so this is the energy of satellite in an circular orbit. Now let us analyze the energy of satellite in an elliptical orbit. So we have already discussed that previously that this distance is r minimum, and r minimum this distance is AE. So r minimum is A into 1 minus E, and this distance is r maximum, and r maximum is A into 1 plus E. And the velocity of the planet, this is called as apogee, which is the farthest point, or aphelion. So velocity of planet at this point is V max, and velocity of planet at this point at perigee is V. This is V minimum, and this is V maximum. And we have already derived the relation that V maximum is under root of Gm by A, where A is semi-major axis, into 1 plus E upon 1 minus E, whereas V minimum is equal to under root of Gm by A into 1 minus E upon 1 plus E. This is the V maximum and V minimum. So now let us write down the energy at perigee. Perigee is this point, this one. So energy at perigee is half m V max square plus potential is minus of Gmm by r minimum. So this is half m into Gm by A, and this is 1 plus E upon 1 minus E, minus Gmm by r minimum, which is equal to A into 1 minus E. So you can see that after taking common the energy at perigee, total energy at perigee is Gmm by E into 1 minus E is common. Gmm by E into 1 minus E, in fact A into 1 minus E is common, and here Gmm by A into 1 minus E is common, and here is 1 plus E by 2. So it would be 1 plus E by 2, and here Gmm upon A into 1 minus E is common, so it would be 1 there. So at perigee, you can see total energy at perigee is equal to Gmm upon A into 1 minus E, and you can see that this is 1 plus E minus 2 upon 2. So this is total energy at perigee is equal to minus of Gmm upon 2A, where this A is the semi-major axis. And you can also check out the total energy at apogee, and the total energy at apogee will also be same. So total energy at apogee, by same process you can check out the total energy at apogee, and it would also be same Gmm minus Gmm by 2A, where A is the semi-major axis. So what I am trying to say is the fact that the total energy in elliptical orbit also remains constant, but total energy in elliptical orbit depends on the semi-major axis. Okay. Now, so this is the complete analysis of energies in an elliptical orbit and circular orbit. And in the next video, we'll be bringing some more concepts of gravitation. Thank you.